Okay, welcome everyone to the AQT colloquium. As you know, we've been doing only external speakers, but Michael is the first one from LBNL because we're going to try to invite more people from LBNL to help disseminate all the different research that we're doing on quantum information to all the relevant persons, because different people in different divisions might not talk to each other that much. Now, Michael obtained master's degree from École Polytechnique and from the University of Minnesota. Then he went to Tufts University, where he worked on quantum simulation and quantum algorithms for quantum field theory and relativistic dynamics. He has kept working on that here at Lawrence Berkeley Lab as the Owen Chamberlain Postdoctoral Fellow. Without further ado, I'll leave you with Michael. We're very much looking forward to your talk.
Thank you, David. Let me share the screen. Okay, can you see it? And can you see my pointer?
Yes.
Okay, great. Well, good afternoon, everyone. Thank you for the introduction. It's a great pleasure for me to tell you today about our research on quantum simulation of quantum field theory, of more generally high energy physics that we're doing here at LBL. Feel free to interrupt me with questions. That's totally fine, even if I'm speaking really fast. We have quite a lot of collaborations on projects related to this topic with researchers from Sandia Lab, and also we have a number of very active graduate students from UCB, also from University of Arizona and New Mexico. So today I will mention projects done with most of these people. Here's our very brief agenda for the day. I'll say a few words about what motivates the research on quantum simulation algorithms for high energy physics. And then I will give kind of a big picture of quantum simulation algorithm landscape and say how the topic of today's discussion fits into this big picture. And then there will be a few technical slides about what exactly we mean by nearly optimal simulation and what algorithms belong to this class. And finally, we'll move to the actual ongoing projects. So let's discuss the kinds of problems in high energy physics that we believe quantum computers may help us to solve. Here, I ordered the problems, roughly speaking, very roughly in the order of growing complexity. So probably the first thing that comes to our mind when talking about quantum chromodynamics, hadrons, would be the particle mass spectrum. And in fact, lattice QCD has been pretty successful in calculating masses of particles, but even in this field, there are some difficulties. And for example, it's pretty hard to get masses of heavy exotic particles, which have a lot of flavors of quarks. Even this can be a very challenging problem at some point. Further, I would say on the list would be calculating hadronic observables, which are basically observables telling us about the internal structure of composite particles, part and distribution functions, which are distributions of momenta within hadrons, and also distributions of transverse momentum, angular momentum, spin, and so on. Actually, DOE is really interested in this topic. We are building new colliders precisely to investigate these observables. And to calculate these observables, you ideally would want to have access to the wave function. That's not something that you can get from Monte Carlo simulations. Moving on through the list, probably in the order of, as I said, growing complexity would be simulations of quark gluon plasma, where you still can use some classical hydrodynamic methods. And the holy grail would be real-time dynamics, calculating scattering cross-sections. And I also wanted to mention in this list applications to relativistic quantum electrodynamics, because when we say high energy, we typically think of QCD and hadrons. But in fact, even in QED, there are problems which are computationally very challenging, such as physics of strong, say, charged particles in strong background fields, or the studies of heavy atoms, at charge like about 100, when we move to super heavy elements, our non-relativistic theory pretty much breakdowns, our simulation methods break down. So we would also benefit a lot from having access to quantum computer. Okay, let's talk now about quantum simulation. I roughly will split this discussion into 3 stages. The first stage is somewhat preparational. Given a physical setting, we need to first pick a discretized model of the system that we will then solve using quantum computer as a very advanced calculator, basically. And on the one hand, the choice of the discretized model is somewhat separate from a quantum computer. If we had access to an exponentially large classical computer, we would solve this very same model without a quantum computer, right? But on another hand, this step, it first of all is very much related to the choice of observables that we want to calculate, whether we want to study, say, bound states, or we want to study scattering at a very high energy. This affects our choice of the system. But the choice of the physical model is also very much related to the computational tools we use and the hardware we have access to. So when choosing a system, we really have to think about many aspects of the whole kind of paradigm in advance. The intermediate step is mapping degrees of freedom in our discretized model onto qubits. This step may be highly non-trivial. Here, error correction comes into play because for the majority of, probably for all realistic simulations of high-energy physics, we will need a fault-tolerant quantum computer. And then finally, we'll move to quantum simulation itself. In most settings, you can imagine that we are interested in calculating some observable in our discretized model in a particular state. And so we map this Hilbert space of our discretized model on a quantum computer. And we hope that we can get in our quantum computer reasonably close to the image of this final state. So we initialize our computer in some initial state, and the quantum simulation brings us reasonably close to the final state. Of course, probably not exactly here, but not too far. And just one remark I wanted to make here. This path in the in a Hilbert space of quantum computer, as we are applying our gates, it may resemble some physical process in the system. So in this sense, it's kind of intuitive, but it does not have to, right? So if we consider discretized time evolution, right, it is kind of intuitive what we do, or say even adiabatic interaction turn on, right? It's like we are turning some knobs in a system if we assume that we can regulate coupling constants. But in other approaches like variational methods, nothing like that happens. Again, the only thing that really matters is that we are in good shape at the end of the calculation and get something sensible. Okay, so on this slide, I schematically depicted the landscape of various families of quantum simulation algorithms. The story begins with algorithms based on product formulas, which embody a very intuitive approach to quantum simulation. In case of time evolution, we discretize the entire time period into small time steps, and then we implement evolution for each time step using a Trotter formula. And something very similar for adiabatic state preparation. In this case, we have short periods of time-dependent Hamiltonian evolution. So during these periods, we also adjust the value of coupling constant. And these algorithms, in fact, not only they're intuitive, but they also have other advantages. So first of all, they do not require ancillary qubits. And beside this, we can actually implement some of these algorithms on existing devices or soon-to-appear devices, at least for some very simple systems. But pretty soon after development of these algorithms, it became clear that for realistic systems, it's kind of unlikely that we will actually use something like this on near-term hardware. So this motivated the development of various near-term algorithms. And here I kind of emphasized or decided to discuss two major directions. One is, of course, variational algorithms, right? So here you use a quantum computer to calculate the expectation value of your Hamiltonian or some other operator in the parameterized state, and you classically run minimization over the parameters. And another very interesting recently developed family of methods is based on the so-called Krylov subspace, or generally they call it sometimes just referred to as subspace methods. So here, in order to learn something about low-lying states in the spectrum of our Hamiltonian, we generate a set of vectors belonging to the Hilbert space. These vectors are not necessarily orthogonal. In fact, they're typically not orthogonal. And then we solve in this limited space the generalized eigenvalue problem. And notice that this approach actually is really very separate from the variational approach. There is no variational optimization here. However, the types of algorithms that we may be willing to use on fault-tolerant devices may have very different philosophy from what we use on near-term devices. And that's something I'm going to discuss now. And as I said, it's very likely by simple counting argument that most likely we will have to wait until we get fault-tolerant devices in order to simulate realistic physics, realistic high-energy physics, because we have way too many particle flavors, degrees of freedom. The Hilbert space is just too large. You know, just to implement a single gate on the entire system, you would probably already need a fault-tolerant qubit. So, what should we like keep in mind when developing these algorithms? It kind of makes sense to first think about the asymptotic complexity of the algorithm, then probably about constant factors, and then about more detailed aspects of the algorithm. So a very large family of nearly optimal algorithms, and I will elaborate the meaning of this word on the next slide. A very large family is based on the following idea. So we assume that we have a circuit that allows us to map a given state, or actually arbitrary state, psi, onto h psi. So we can implement this transformation h, and h here is not unitary. In most applications for us, this will be the Hamiltonian. And then these algorithms allow us to construct the application of some function of a Hamiltonian. This can be exponent, or this can be something that helps us to get the ground state of the system. So this will be a large portion of today's discussion. But constructing something like this is actually pretty hard. And another recently developed family of algorithms relies on this idea of Hamiltonian time evolution axis. So here, the building block, instead of a circuit that implements the action of h, is the circuit implementing one step of time evolution. And also from here, we go to implementing some more complicated function of f. Few notes for this slide is, first of all, these families are by no means disjoint. Like these blocks here are more like vectors, which can be taken in superposition. So you can combine these approaches in various ways and get very fruitful results. And make some variations. For example, say for variational algorithms, you can use them not just for calculating the ground state or few lowest state. No, you can actually use them to simulate real and imaginary time evolution as well. You can use nearly optimal algorithms for calculating ground state energy without actually implementing some complicated function of the Hamiltonian. So you can use these methods that we discuss here. And lastly, you can actually combine subspace methods with algorithms on this side. So you can use block encoding and time evolution in order to construct these subspace here. And I wrote this in bold because I actually believe that this is an extremely promising approach for near-term applications. Using subspace methods based on time evolution axis. That's I think something that we'll be able to do for simple systems, maybe a year or two, or maybe even now. But for this talk, as I said, we're focusing on nearly optimal algorithms because that's where high energy physics applications are. Okay, so what do we really mean by nearly optimal? When I say this word, what does it mean? So let's consider the asymptotic complexity of a typical algorithm for Hamiltonian time simulation based on product formulas. And let's say we count the total number of gates or the number of C-naughts, doesn't really matter. So in terms of asymptotics, this number will scale superlinearly with time. So it's some polynomial of degree larger than 1, and polynomially with inverse error. And you can do various optimizations and adjust these powers, but that's the rough idea. I also note that the Hamiltonian norm always accompanies the time, because for time evolution, you can always trade one for another. You can rescale the Hamiltonian, but then the cost of it, you evolve for longer time. So one very important result in quantum simulation is the so-called no fast forwarding theorem, which states that it is highly unlikely that we can simulate an arbitrary Hamiltonian with complexity with scaling, which is better than linear in time. Basically, this violates some hypotheses that a lot of very smart people believe hold true. So a natural question then, okay, then how do we reach this asymptotic scaling with time? How do we get rid of this and make scaling linear? So that's one question. And then the following question would be, how do we reach good scaling with error and with other problem parameters, Hamiltonian norm, Hamiltonian sparsity, problem size, and so on. So if we assume that access to fault-tolerant device, we should probably start, as I said, with asymptotics. Okay, when we're done with this, and when we believe that we developed some algorithms with good asymptotic scaling, probably we should also worry about the constant factors, right? Then we move there. And then finally, if we believe that we optimize this and that, then it's probably time to run some actual tests and compare these methods to more conventional approaches, such as those based on product formulas. So that's the three questions that kind of drive this entire research. So as I mentioned before, many, if not majority of nearly optimal algorithms are based on this concept of being able to implement a function of the Hamiltonian, given that we can implement the action of the Hamiltonian on a state itself. So for definiteness, let's say we want to simulate time evolution. Let's say this is our goal. And let's zoom out, make a step back, and consider for a second a more general problem. Let's say we want to implement some function of h, not just an exponent. And the first step on this path is the ability to implement the action of h itself. And this is achieved using the subroutine or maybe construction known as block encoding. It's most easiest to understand what block encoding is using matrix language. So let's say h is some matrix. It's not unitary. In our applications, it's Hermitian, but that's not even required. So let's place this matrix in this top left block of some unitary, which of course requires already that h has to be normalized, because all the entries of a unitary matrix, they have to have absolute values smaller than 1. That's a necessary condition. But let's say we did this. And then let's do the following simple calculation. Let's act with this matrix onto a column vector x. So x is the state of the system we're interested in. And here we have 0. There's some extra dimensions, which we'll get using ancillary qubits. And then the result is the vector which has hx in the first component and some garbage here that we do not really care about. And then we can just formally split it as a sum of two vectors. So we kind of managed to get from here to here. Okay, now let's discuss this, how this works at the level of operators. So the block encoding operator acts on the extended Hilbert space. So we have the state of the system and the ancilla. And the result is two terms. So one of the terms is precisely what we want, h psi, h applied to psi in the first qubit, tensored with 0, and some garbage. The only thing that we require about this garbage is that it has to be orthogonal to the ancillary qubits. And the reason why it has to be orthogonal is actually clear from this circuit. So this circuit is how we apply the block encoding in practice to get from psi to h psi. So we have this circuit here, state of the system, ancillus, we apply block encoding, and then we measure the ancillary qubit. So if we measure the state 0, if we measure, if the outcome of the measurement is 0, all the qubits are in the 0 state, then it is guaranteed that we landed in this state of our physical system. Why so? Because by construction, this garbage is orthogonal to the state 0. So if we wrote down this perpendicular component in terms of basis vectors, none of them would have 0 component. So we have to be here. And if we get something different from 0, well, we just, disregard the outcome of this calculation and restart it and go again. Of course, this implementation, first of all, requires ancillus, and second is probabilistic. The probability of success may be pretty low, but in most cases, there's a way to make this success probability of order 1 by trading the lengths of the circuit. So we can make basically repeat this application several times and use an algorithm called amplitude amplification, which essentially is just the Grover search. So we make circuit longer, but we reach high success probability. Various ways to constructing block encoding exist. One way, of course, is to just explicitly write down the matrix of the Hamiltonian and decompose it into elementary gates. This is not really scalable. We cannot do this for the entire Hamiltonian of a large system, because then what's the point of quantum simulation if we can just explicitly write the Hamiltonian? But this approach is useful as a building block for other approaches. So, for example, we can study in great detail the matrix of the Hamiltonian on local site, compose some block encoding, and then use other methods to scale it. The two major approaches to constructing block encoding, though, are the algorithm called linear combination of unitaries and using the sparse access oracles. So we'll briefly mention those. So linear combination of unitaries is a very, it's a highly useful routine that is utilized in a large number of simulation algorithms. The setting is the following. So let's say we have some Hamiltonian operator, which we can write as a sum of unitary operators with some coefficients. And at first, this setting may seem to you somewhat artificial. At the end of the day, why would some Hamiltonian operator have some simple expansion instead of unitaries? But just recall that the Pauli operators themselves, they're not just Hermitian. Each Pauli operator is also unitary, x, y, and z. So as long as you have the expansion of your Hamiltonian in terms of qubit operators, you're good. So you have this starting point. And let's say we have here big K operators. And so LCU is a routine that precisely gives you the block encoding.
Would LCU fail for Q-treat systems?
I actually think that this should exist, but this should also be relatively undeveloped. I mean, I don't see any problem why this would not work. Yeah, this would definitely work. Yeah, we would just have to have multi-controlled gates on Q-treats, and I know nothing about that. But in principle, yeah, this would work. The essential idea of LCU is that we sequentially apply all these operators, and each of these guys is multi-controlled on a unique set of zeros and ones in the ancilla. So typically, we use some kind of binary encoding. So let's say if we have 4 terms, we have 2 ancillas because there's 2 to the power 2 possibilities. But if, say, we had 9 operators and we had Q-treats, then we would only need to have 2 ancillary Q-treats, right? Because 2 Q-treats would give us 9 unique basis states, and we would control each of these 9 operators on one of these combinations. Did it answer your question?
Yes, thank you.
Okay, good. Yeah, thank you for the question. Of course, we typically forget how exactly LCU works, but some useful outcome to remember is the good news about this kind of traditional LCU approach, which I just described now. The good thing is that the number of ancillas is only logarithmic in the number of operators here, right? This is good. The bad news, however, is that each operator is multi-controlled or on all ancillas. That's typically comes at a great expense. So if possible, we would like to avoid such things even on fault-tolerant computers. So I would also like to point your attention at some very recent work. That's something that IBM guys rolled out maybe a couple months ago. Here, they use a different approach to encoding ancillas, and instead of log k ancillas, they actually have 2n ancillas, where n is the total number of qubits, right? So essentially, you triple the dimension of your, triple the number of qubits that you use in your circuit, right? Which seems a bit weird. But if your terms are local, if it's guaranteed that each unitary here acts on at most m qubits, then the resulting circuit contains only multi-controlled gates acting on 2m ancilla qubits instead of log k. So this interesting idea about different encoding of qubits. Yeah, so one thing to remember is that it's expensive in terms of control gates, and the other fact is that the complexity of the length of the circuit will scale inversely with the one norm of this vector of coefficients. Basically, there's a simple relation between one norm of this vector and the norm of the Hamiltonian. So that's one approach, pretty general. As I said, if we have access to the qubit Hamiltonian, we can immediately construct this. The other approach to constructing block encoding is based on the so-called sparse oracle access. So oracles are quantum circuits which provide you in some form the information about the matrix elements of the Hamiltonian operator. So as input, the oracle literally takes the indices of the column and of the row of the Hamiltonian matrix. So you have ith column, ith row, jth columns. They come as input, and nothing has done to these guys. So they are accessed, but they remain unchanged. And then Oracle tells you the information about the corresponding matrix element, and it can be queried in various forms. So for example, in this formulation, it's in the binary form, and here it's given in terms of amplitude, and we can efficiently switch between these two approaches. What matters, though, is if you have Oracle, then constructing block encoding is easy, but constructing the Oracle itself is hard. So we're kind of sweeping things under the rug and trading one complicated problem for another. But you know, going this path may have its own advantages, as we shall discuss later. Okay, so at this point, we assume that we know how to construct the block encoding for a given Hamiltonian. So we assume that we know how to do this step. The question is, how do we move on? How do we now implement the function of the Hamiltonian to the target state? So this is accomplished by this fairly known algorithm, quantum eigenvalue transformation, which is very closely related to the concept of qubitization. So sometimes I will use these words interchangingly. So this circuit accomplishes the following. Given a polynomial of degree n, it uses the circuit of the following pretty simple structure. So we just repeatedly apply this block encoding, and we interchange U and U dagger if this unitary is not Hermitian. And also we have here a bunch of controlled phases. The number of controlled phases in this circuit is precisely equal to twice the degree of the polynomial that we want to apply. So the algorithm is the following. We take the polynomial, expanded in terms of Chebyshev bases, Chebyshev polynomials. So in this case, we're not using monomial basis, but we use an equivalent basis of Chebyshev polynomials. And from these coefficients, one can efficiently calculate the phases here. And then this circuit outputs the block encoding for the desired polynomial. So let's recap. If we want to implement the action of a function of some operator on a state, for a pretty wide class of functions, the first step is we expand this function in terms of Chebyshev polynomials, get their coefficients. From the coefficients, we get those phase parameters. Second step, we construct the block encoding. maybe using LCU, maybe using Oracle Access, maybe we invent something better in the next few years. And third step, we use this QET circuit to combine those individual block encodings into this big circuit. Why did we do all of that? What did we achieve? So as it was advertised, first of all, we're getting some asymptotic advantage. So that's something that we have already discussed. That's for time evolution, the asymptotic complexity of product formula. In the best case scenario for quantum eigenvalue transformation, we get something like this. So we have linear scaling with time and Hamiltonian norm, and we have logarithmic scaling, which is significantly better than polynomial scaling with inverse error. Moreover, they come here with a plus sign. And the first algorithms, they actually contained product, and there was like years and years of development to go from product to sum here, because clearly this has a better scaling. And we have similar bounds for ground state preparation algorithms and for ground state energy estimation algorithms. Now, these two algorithms are actually much harder to compare with existing techniques based on product formulas, which are typically use adiabatic state prep, just because it's much harder to prove some bounds here. So essentially, if you want to do some fair comparison, you just need to pick some model and run the simulation. So it's really very much an open question. Even though I should say there have been a lot of interesting results recently in this direction. All right, and at this point, let's switch gears a little bit. So far, we've only been talking about algorithms, or at least for some time since the motivation slide. Now, I would like to talk about various formulations of problems in physics, because as I said, choosing a particular formulation as a starting point for quantum simulation, has its own consequences. So we better realize what those are. So we oftentimes distinguish between the so-called first quantized and second quantized approach to many-body quantum mechanics. In terms of discretized systems, for the first quantized approach, so here I use example from quantum chemistry. In the first quantized approach, we discretize the space, so we have lattice sites, and we also discretize the field values on each lattice site. And in the second quantized approach, we are working in the basis of creation and the basis of number operator of the theory. So what our qubits store is the occupancy of what chemists would call orbitals, or what physicists would call modes, like momentum modes or other modes if we have different bases. So let's compare these two formulations. Well, first of all, this formulation is local, at least if the potential is local. So if we have delta function here, then again, at the level of fermions and bosons before mapping onto qubits, this formulation is local. The second quantized formulation is clearly non-local. So in general, any two operators, any two modes or orbitals can be related to each other. The second important circumstance is that first quantized approach may be not so good for simulating highly bound systems. That's why you never or almost never hear quantum chemists talking about discretizing space. That never even come to their mind until quantum computing guys suggested it to them, probably. Instead, they use very highly optimized basis sets, and not only quantum chemists, actually, nuclear physics guys and even high energy physics guys, they do this. So, and this is another pretty big distinction. Next parameter on which we can evaluate various formulations would be the number of elementary terms in the Hamiltonian. So how many terms, each of which is easy to simulate, do we have in the expansion of the Hamiltonian operator? So here, clearly the first quantized formulation wins. If the potential is local, then the number of terms scales linearly with the number of sites. If the theory is non-local, say we have Coulomb interaction, then the number of terms would scale as n squared. Now, on the second quantized side, the number of terms would generally scale as n to the power 4, right? Because we have for quartic interaction. So it will be n to the power whatever degree of the interaction we have. So here we have the sum over ijkl, right? So the overall number of terms from this group will be n to the fourth, unless the interaction is local and we work in the plane wave basis, because in this case, due to momentum conservation, we would have an extra delta function. So it would give us actually n cubed. And this circumstance, this, I would say, this parameter, it's important for both LCU-based algorithms and actually also for Trotter-based simulation, right? Because in product formulas, we exponentiate each individual term. So here it's kind of similar. We in both cases, we care about the number of terms in the Hamiltonian. Another circumstance, that's something that we care about when constructing oracles, is how complex are the coefficients next to these terms. And if we have a lattice field theory, the structure of the Hamiltonian is typically very similar. So, you know, what's going on each lattice side is precisely identical for all the lattice sides. But if you work in the momentum basis, then the coefficients next to your creation and annihilation operators for momentum modes may themselves depend on momentum. But for plane wave basis, at least this dependence would be simple. But if we switch to some very weird basis, then this dependence may be way more complicated. So what we learn from this kind of big picture of models is that in applications to high energy, probably the first choice would be doing lattice formulations of QCD. And if we do second quantized approach, probably start at least start with a plane wave basis. Okay. Congratulations, we survived the theory part. And now, in the remaining time, we'll talk about the applications. So the first two projects are somewhat technical, what we do with the guys from Sandia. So I will just highlight some interesting things and maybe give a very, very big, like high view overview. Then I'll talk about the projects that we do with Berkeley and University of Arizona students. So this will be slightly more entertaining. So the first project addresses the calculation of properties of relativistic bound states, primarily the calculation of spectra. The particular example that motivated us is the particle that's considered as a standard model candidate for dark matter, right? Most proposals to dark matter particles, they are beyond standard model, but in fact, there is a very interesting possibility that such a particle is actually what we call like absolute scalar sexy quark. And believe it or not, we still cannot even have a good estimate for the mass of this particle using lattice simulations. We have too many degrees of freedom. So that would be a very good like problem to solve using quantum computers. The particular theoretical formulation of quantum chromodynamics that we use here is called light front formulation or light front quantization of QCD. It's a formulation that's highly suitable for studying relativistic bound states. In essence, it makes look relativistic physics very much like non-relativistic physics, so almost like quantum chemistry. The only thing that I really wanted to mention in regards to this project, which, as I said, is pretty technical, is the following. So we have second quantized Hamiltonian, and we work here in momentum basis, right? So we have generally fourth order interaction term. Those can be fermions, bosons, and as we just discussed, we have momentum conservation. So overall, the number of terms scales as number of modes to the power 3. So if we were using LCU, or if we were using Trotter, in the final algorithm, the number of gates required to implement a single step would scale as n to the power 3. But it turns out that using the oracle access model, you can actually implement a step of time evolution with complexity linear in the number of modes, which to me, honestly, was a little bit mind-blowing. And it takes a little bit of time to understand how it works. But yeah, that's kind of the magic of quantum computer. Okay. Now, in the second project that we also do in collaboration with Sandia guys, we address the question of whether we can benefit from the locality of Hamiltonian, and we know that there are local formulations of lattice gauge theory, whether we can actually benefit of locality of the Hamiltonian when designing a quantum simulation algorithm. Because naively, neither LCU nor Oracle Access approach take advantage of this. So how do we proceed? Well, the best known algorithm for simulating local Hamiltonians, and the best, of course, I mean, in the sense of asymptotic complexity, it's called, after the last names of authors, HHKL, the HHKL algorithm. And it has complexity that is linear in time. So that's already optimal, or nearly optimal because of this logarithm. And its logarithmic is in 1 over epsilon, 1 over error. So this is almost as good as quantum eigenvalue transformation, right? And as a building block, this algorithm assumes access to the time evolution blocks to time evolution circuits for local blocks. So imagine we have a local theory, and from let's say given by God, we have blocks which allow us to locally simulate time evolution here, here, and here. And then HHKL tells us how to combine these blocks in a very efficient way. So it's like a very, very smart way of trotterizing things in a way. So as I said, each block has to be implemented exactly, or at least in a nearly optimal way, which implies that in practice, we would still need to use algorithms based on block encoding to implement evolution for local side. So everything that we discussed before will still be useful, but will be done locally, and then this will be combined. And then another important circumstance is that, of course, in a physical theory, the matter fields are fermions, right? And if you map fermions onto qubits, they become non-local. They become maximally non-local if you use Jordan-Wigner transformation, right? If you basically the string of those Z operators that ensure the correct commutation relations can be as long as the number of all degrees of freedom in your system. So this clearly doesn't work. And typically we just make a footnote, but you could use Bravik-Kitaev. Okay, but Bravik-Kitaev has locality, which is logarithmic in problem size. And in this case, it doesn't work because for this formulation, the qubit Hamiltonian has to be strictly local. So here, the only opportunity really is to use this method by Verstraete and Sirac, which allows to map local fermions onto local qubits. And in this method, you have to actually double the dimension of your Hilbert space and introduce some ancillary interaction. So that's a very, very technical project that we are kind of doing with Sandia guys. Okay. Now, in the third project, we are actually running performance tests, and we are comparing the complexity of product formula-based approaches versus these nearly optimal approaches. So I will show you a couple of plots that were just recently generated by our grad students from UC Berkeley, Neil and Sid. So as a particular benchmark, let's consider something very basic, just phi 2, like harmonic or anharmonic oscillator, which for physicists it's like a bosonic field theory on a single lattice side. And for anharmonic oscillator, we'll consider pretty strong coupling regime, but that's not very important right now. So to get the discretized model, we digitize the field values, right? We do this lattice approach. And when we digitize field values, we want to ensure that this range of values overlaps with the span of the ground state wave function. And it turns out that for this choice of constant, actually, there is a range that works for both harmonic and anharmonic oscillator. And we will just use 2 qubits per side. So the question is, which one is better? So here you see the plots for the number of CNOT gates as a function of simulation time and as a function of error. So this axis is simulation time, the error, and the preparation of the final state, and the number of CNOTs, which is, of course, very large. So what do we learn from these plots? Well, as expected, for QET, the number of gates scales linearly with both time and with logarithm of the error. And for product formula, it scales polynomially with time as a very low degree polynomial. and polynomial with error. So when does it make sense to use QET? When is the number of gates lower? Well, one way you can achieve this regime is to kind of push the desired error. So as long as you say that you want some crazy precision, of course, you will run into the zone where it's better to use quantum eigenvalue transformation, because log 1 over epsilon is a huge advantage over 1 over epsilon or some polynomial of 1 over epsilon. So you can easily get here, but notice that if the required precision is not too high, then you may actually need to consider time evolution over very long periods of time until you finally reach the point where it makes sense to use quantum eigenvalue transformation. And this is a very general pattern, but of course, we want to do similar tests once we already developed all this machinery for more complicated systems, and mainly for systems with a large number of sites. And another important direction would be to use this machinery that we have for ground state preparation algorithms, to compare this with adiabatic and with something that we'll discuss on the next slide. Okay, and here we reach the fourth project. And here we explore the approach to nearly optimal simulation that's somewhat alternative or complementary to block encoding. So the bottleneck of all those nearly optimal algorithms I've talked about so far is the construction of block encoding. The Oracle or LCU are both very expensive. So what else can we do? How can we overcome this complexity? So this problem, that the very high cost of block encoding, it motivated the development of approaches to ground state preparation and ground state energy estimation, which can be actually quite different algorithms, which is based on the Hamiltonian time evolution access model. So here, the building block is not block encoding for Hamiltonian, but instead is just one block of time evolution, typically for some very short time. And in the original version of algorithm, we assume that we can implement this time evolution exactly. So can we develop any nearly optimal algorithms using this as a basic ingredient? Yes, we can develop algorithms for ground state energy estimation. And in this case, we can actually be extremely efficient. And it's enough to have as little as just one application of time evolution for a few very small times. We can also do quantum eigenvalue transformation and use it for ground state energy preparation. Now, this circuit is actually very much reminiscent of the QET circuit I showed before, but instead of block encoding, we just have here this block of time evolution. So this circuit I will refer to as QETU. So ground state preparation, the particular approach to nearly optimal ground state preparation that I will talk about now is based on the so-called idea of filtering. The idea is actually very elegant and simple. So imagine that you have access to the projector on the ground state of your system. And imagine that you have some state with non-zero overlap. Let's call it reference state. So we have reference state with, has some non-zero overlap with true ground state. Then life is easy. You just apply the projector to this state and you get the ground state. Okay, but then you ask, okay, how do I get such a projector if I don't even know what the ground state is? Well, it turns out that you can approximately implement such a projector with just a little bit of information about the spectrum of your system. So if you don't have to know precisely your ground state or first excited state, but you need to know, in the most simple case, some energy value in between the ground state and the first excited state. And then the following transformation, this step function, would precisely suppress all the coefficients of your expansion of the Hamiltonian in terms of in this eigenbasis, which are higher than this value. And the only remaining thing will be the projector on the ground state. So we will use QETU circuit to implement this function of the Hamiltonian operator. And this function will give us the projector. So again, these are some plots generated recently by Chris. So Chris K is a student at University of Arizona. And the first thing, we just want to make sure that the algorithm actually works in principle, that it works in this exact form. And for a small number of qubits, nothing stops us from implementing e to the power IH exactly. So we see that as we increase the degree of the polynomial, the closer and closer we are to this sharp step function, the closer we are to the true ground state, right? So that's good news. If this did not converge, that would be sad. But in reality, we cannot implement time evolution exactly. So most likely we'll use product formulas. So with our discretization step, the way we implement time evolution for harmonic oscillator using product formula is the following. We split the Hamiltonian in two parts, each of which can be trotterized exactly. So we have a part with everything that's x dependent, and this part is diagonal in the computation basis, so we can implement it exactly. All the terms commute with each other. And the other part, the momentum term, it is also diagonal, but in the momentum basis. And we switch between position and momentum basis using the Fourier transform. So this can be implemented exactly, this can be implemented exactly. But these two guys do not commute with each other, so the error in your approximation is given precisely by the number of steps here. So let's run the simulation and try to, again, achieve the ground state, but using this approximate implementation of time evolution. And so we see that as we increase the degree of the polynomial in our approximation of step function, we saturate at a certain value of error. And this happens precisely because the implementation of time evolution is not exact. And so the higher the degree here, the more steps we have, the smaller the error is. And we can actually study the dependence of this error on the number of steps. So let's just put on the plot these points. And just as expected, we see that this dependence is polynomial with the number of trotter steps. But that's not quite trotter steps, but the analog of trotter steps. So that's what we would expect from the algorithm, which involves product formulas. And in this sense, this algorithm is no longer nearly optimal, but still it can be, at least for certain ranges of parameters and certain systems, may be more useful than trotter-based approaches, the naive trotter-based simulations. So, of course, here the next step for us is to move to larger systems, to more complicated field theories, and to compare the results of this ground state preparation algorithm with adiabatic state prep, but also with truly nearly optimal approach that relies on block encoding. Well, that's actually the end of my talk. Pretty much I talked about everything I wanted, and thank you for this opportunity. I'm really glad that I could present this work, and I'm open for questions.
Thank you very much. It was a very interesting talk. Are there questions or comments from the audience?